Okay, good morning and welcome to today's lecture. In the last few lectures, we have looked at the atmospheric water, in which we looked at the formation of rainfall, various types of precipitation or forms of rainfall. Then we looked at the representation of rainfall, that is mass curve analysis, heatograph and maximum depth duration curve. We also looked at the evaporation in the last chapter, empirical methods, analytical methods and some experimental methods for estimating evaporation. Today we will start the next chapter, which is on surface water. Okay. What happens to the rainfall when the rain is falling on a catchment? All right. What we will try to do in this chapter is look at different types of storage components in a catchment, look at the rainfall runoff process, how the rainfall gets converted into runoff. Okay. We will look at various definitions involved with a hydrograph, then we will go to some mathematical modeling of the rainfall runoff process. All right. So, first let us get started with the chapter on surface water. As the rain is falling, what happens to it is it gets stored in different storage components. All right. We have discussed this earlier, and these storage components will have different storage capacities, and depending upon the storage characteristics and catchment characteristics, it will be able to release the water from these storage components. All right. So, if we look at it here, we have the rainfall P falling on the catchment, then the catchment basically consists of lots of storage components. All right. And out of these storage components, then we have the output coming out from the catchment is what is called flow, stream flow, runoff, etc. Okay. In any mathematical model of rainfall runoff process, basically we try to model this storage characteristics of the catchment. All right. It consists of various types of storage components. First one of them is what is called interception. What is interception? Interception is the storage of rainwater on the forest cover or the leaves and branches of the trees. All right. This interception storage gets evaporated after some time and lost into the atmosphere. All right. There will not be any runoff directly from this before the interception storage capability or capacity of the catchment is satisfied. Right. So, that is interception storage. There is another type of storage initially in the catchment, which is called depression storage. Right. What is depression storage is the water stored in a catchment in the various depressions on the landmass, or the puddles or small lakes, or some obstructions, buildings, etc. So, the interception and depression storage has to be satisfied first of all before any runoff can occur from a catchment. All right. So, these are the first two storages, and then what comes out of this is what is called the overland flow. All right. So, let us say there is sufficient supply of water due to rain. What will happen is that the interception and the depression storage capacities of the catchment will get completely satisfied. After that, you will have water running down into the ground, and then it will start as the overland flow. Then we have water getting stored into the surface storage. On the surface of the land, we will have water getting stored, and once that capacity of surface storage is satisfied, we will have the flow coming out of this. Another example could be the channel storage. All right. The water that is stored in the rivers and streams and creeks, etc. What comes out from these storages is what is called stream flow. Okay. Stream flow that we observed in the rivers and streams. All right. What is the another type of storage apart from these 4 storages? Water goes into the ground, all right. And then what happens to the water that goes into the ground, that it can get stored into what is called the soil storage or soil moisture. Okay. When the water gets stored into the soil moisture storage or soil storage, it gets transpired or it gets lost into the atmosphere through the process of evapotranspiration, which we have looked at in the last class. Okay. If there is a sufficient supply of water available in the soil storage, it can come out as what is called interflow. Okay. I think all of you understand what is interflow, all right. It is the movement of water in the unsaturated zone of the ground or the subsurface strata of the earth, all right. When there is sufficient supply of water, what can happen is that water can travel laterally and appear as interflow into the creeks and rivers. Okay. Another type of storage is the groundwater storage. From the soil moisture storage, what may happen is the water may get deep into the groundwater through deep percolation, and how does it come out into the surface? In the form of base flow. Okay. So, we see that there are different type of storages in the catchment, all right. As the rain falls, all these storages will get satisfied or this will get filled up, and these storages will have different mechanisms of releasing the water, and that is what is involved in the rainfall runoff modeling. Okay. Now, we come to the classification of these different types of storages. All the storages which we have looked at can be classified broadly into 2 kinds. One is called the retention storage and other is called the detention storage. What is the difference in retention and detention? As the name suggests, in the retention storage, the water gets stored in that particular storage for long periods. All right. So, water is retained for a longer duration, and how it is depleted? It is depleted by evaporation. Okay. Can anybody think of the example of retention storage? It is the soil moisture storage. For example, water gets retained in the soil moisture for longer duration, and then it can get evaporated or transpired, evapotranspiration into the atmosphere. Okay. So, soil moisture storage is an example of a retention storage, and also the groundwater storage. The other type of storage classification is what we have as detention storage, which is for short duration, as the name suggests. Okay. And how is it depleted? It is depleted by either evaporation or the outflow, you can say, or flow out of that surface storage. For example, we have flood control structures or detention basins. All of you may have heard about them. What is a detention basin or a detention storage? When there is a lot of water coming in into the catchment due to rainfall, what we do is we temporarily store the water in the detention storage or the detention basin, all right, and which will have an outflow structure over which, after sufficient the capacity of the detention storage is satisfied, we allow the water to overflow over a weir or spillway or something, all right. So, that is called the detention storage. Okay. Another way to look at this is as far as the kind of storages in terms of periods of retention or detention. Another way to look at the different types of flows is either Hortonian overland flow concept versus the saturation overland flow concept. Okay, these are two different theories, we can say, which try to model the infiltration or the abstraction from the rainfall. All right, this Hortonian concept was proposed by Horton in 1933. Okay, so we are going to look at this first. So let's say we have Hortonian flow. When do we have Hortonian overland flow or Hortonian flow? He basically proposed that the runoff from the catchment can be calculated by simply subtracting infiltration from rainfall. Okay, so it is not accounting for any other type of losses. So mainly the infiltration losses, and what he proposed is that if we want to find out or estimate how much runoff will occur, we just take the total rainfall and estimate the infiltration somehow and we subtract it. So that was the first time he proposed, and this is called the Hortonian concept of overland flow. The important thing to remember in this Hortonian overland flow concept is that the catchment is saturated from top. What do we mean by that? Let us look at this figure. Let us say you have a catchment in which the rain is falling. What you will have is water getting ponded, all right, and then this is your river or some creek, all right. What will happen as the rain is falling is water will infiltrate into the ground. Okay, so let us say your intensity of rainfall is I, all right, which may be a function of time, and the infiltration rate is F, all right, and we have seen some of these things earlier. And what will have is you will have the Hortonian overland flow going directly into the river as the overland flow. So when I said that in the Hortonian overland flow we have saturation from the top, that is rain is falling on the ground and getting infiltrated into the subsurface zone, and which is saturating the subsurface zone from the top, all right, or water which is infiltrating from the top. Okay, so that is the main important concept in the Hortonian overland flow, as opposed to the saturation overland flow, in which the ground is saturated from below. Okay, what do we mean by that? So we may have a situation like this, all right. So rain may be falling in some hilly areas in the upstream reaches of the catchment, all right. Then what may happen is that this water may get infiltrated into the ground, and due to the steep catchment slopes in the hilly areas, this water may travel inside the ground, all right, and that will saturate the subsurface zone of the earth in the downstream portion, all right. And then later on, when you may have rainfall falling in the downstream catchments, the subsurface zone is already saturated, but this is saturated from below, that is already moisture is there due to rainfall or some other reason through the interflow coming in into the subsurface zone. So this type of overland flow, then you will have this ponding taking place due because the subsurface zone is already saturated, and you will have the overland flow. So the mechanism of modeling of the overland flow will be quite different for Hortonian overland flow and the saturation overland flow. Okay, the Hortonian overland flow is applicable to impervious areas or natural surfaces with low infiltration capacities. Okay. These type of conditions will be available in semi-arid and arid areas. Okay. And as you can imagine, the saturation overland flow will occur mostly in the hilly areas where the catchment slope is very steep, that will encourage the subsurface flow or the interflow, so that the ground can get saturated early. And you can also say steeply sloped catchments. Okay, so these are the basically two concepts of modeling the overland flow. One is through the Hortonian and other is through the saturation. In most practical applications or most of the hydrological models, commercial software which we see today, they employ Hortonian overland flow philosophy. Okay. Next, we move to a different concept called variable source area. And this is applicable for saturation overland flow. As we can see that, as the name suggests, what is the variable source area? Okay. We are observing runoff at the outlet of a catchment, okay, due to rainfall, and the subsurface zone is saturated from below, all right, due to some reason, rainfall upstream in the catchments. So at any given point of time, the amount of area or the fraction of the area of the catchment that is contributing runoff at the outlet will be different. All right. During a storm, initially, for let us say initial first hour, only small portion of the catchment will be contributing runoff at the outlet. Next 2 hours, larger area of the catchment will be contributing runoff, because more subsurface zone will get saturated later on and more amount of surface runoff will be coming in. All right. So this is basically what we say is that not all of the watershed or catchment contributes runoff at the outlet initially. Okay. The fraction of catchment contributing runoff increases with time, as we can see. All right. So this is what is called the variable source area concept, in which the area that is contributing runoff at the outlet is varying with respect to time. All right. So the modeling of this type of physical phenomena is much more complex, and that is undertaken in the hill slope hydrology. All right, which is not part of this course. So we will not be focusing too much on this. Okay. Next, we move to basic concepts of what is called a stream flow hydrograph. So what we will be doing from this point on in this course is we will be looking at the Hortonian overland flow only. Okay, will not be doing the saturation overland flow in this course. All right. So what is a stream flow hydrograph? I am sure all of you have seen what is a stream flow hydrograph in your undergraduate hydrology course. Okay. It's simply a graph or you can represent this in the form of a table, okay, of numerical values showing what the flow as a function of time. Okay. So, the graph between Q and T is what we call a stream flow hydrograph, all right, and this stream flow hydrograph is observed or measured at a particular location in the river. Okay. Particular location, as we know, is called the concentration point in a river. A stream flow hydrograph gives us a lot of information about the catchment, all right, because it essentially represents the response of a catchment to rainfall, or when a catchment is subjected to rainfall event, how it responds, all right. How it responds means there are various storage components, as we have seen, and how these various storage components behave as a function of time, how they store the water, how they release the water, and how they contribute runoff at the outlet, all right. So, that this whole concept is your rainfall runoff process. So, ultimate results is your stream flow hydrograph, and the shape and size and the characteristic of a stream flow hydrograph will tell a lot to us about the characteristic of the catchment. Before we move to the modeling of a rainfall runoff process, let us look at the types of hydrographs. Okay. Hydrographs can be classified into two kinds, broadly speaking. Okay. First one is we call annual hydrographs, which you all understand, in which the time frame is one whole year. Okay. So, it is a Q versus time in days, let us say, for the whole year, as opposed to what is called a storm hydrograph. And in a storm hydrograph, what we have is for a short duration, all right. So, we have Q versus T for a short duration for which rainfall occurs. Let us say you had a intense rainfall storm for 3 hours. Okay. So, as a result of that force or that rainfall being subjected to the catchment, all right, how the catchment will respond in terms of stream flow hydrograph, that is called the storm hydrograph. Okay. So, we will come to that later, but first let us look at the annual hydrographs. Okay. Further, the annual hydrographs can be divided into three different kinds. Okay. First one is called perennial, okay, or a perennial hydrograph, in which you have a river or a creek or a stream in which we have water throughout the year. You see that on the x axis we have time, and this is your Q of flow in the river, all right. So, you see that the flow never touches 0, all right. It's never 0, there is always some water or always some flow in the river, all right. So, when we have this kind of hydrograph from a river, that is called a perennial hydrograph, and that kind of river is called a perennial river, okay, as we all know. Where is this water coming from in the river? It is mainly from the base flow. So, it has significant base flow or groundwater contribution, okay, in the perennial rivers or in perennial hydrographs. Then the second one we have is what is called an intermittent hydrograph, in which you have flow in the catchment or in the river for most of the year, except very few periods when you do not have any flow in the river, all right. This type of hydrograph on an annual basis is called the intermittent, because the rain is occurring intermittently, all right. And where is this water mainly coming? Then again there is some groundwater contribution. Okay, there is not a whole lot, all right, because sometimes the flow will touch 0 value on the annual scale. All right. The third one is what is called an ephemeral hydrograph. All right. What is ephemeral hydrograph? It is a hydrograph in which you will have just spurts of flow which are separated by long intervals of no flow. All right. So, there are longer intervals of no runoff in the river in ephemeral streams, and this basically means there is hardly or no groundwater contribution in the ephemeral streams or in the ephemeral annual hydrographs. All right. So, this is about the annual hydrographs, which are of 3 different types. Again, to summarize: perennial, in which there is significant contribution from groundwater; there is intermittent, in which there is some contribution from groundwater in the form of base flow; and ephemeral, in which there is no contribution from groundwater. Now, we come to the storm hydrograph. What we will do is, we will define various components of a storm hydrograph first, and then we will look at these different components more closely. Okay. So, as you all know, this is time and this is your Q. We will define various points on the storm hydrograph. Okay. What we normally do is, we plot the effective rainfall heatograph on top, which produces this storm hydrograph. All right. So, this is your ERH, and this time duration is called TR, or the duration of the rainfall. And we will define some more things here. In the form of time, it is TPK. From here, it is TB. We join the line, the beginning of the hydrograph B and the end of the hydrograph E. So, anything above this line, as we all know, is called runoff, and anything below is called base flow. Okay. All right. So, let us look at different portions of this hydrograph. AB is the base flow recession. Okay. And AB actually is coming from the previous hydrograph. All right. This particular hydrograph is rising from B. All right. So, B is the beginning point. So, you can say AB or maybe EF. All right. It is the base flow recession component. Okay. And then you have B to C is called the rising limb of the hydrograph. The portion C, D and P is there in between, the peak discharge, is called the crest of a hydrograph, and P is the peak flow DE is called the falling limb of the hydrograph. TR is the storm duration. For the hydrograph, TPK is the time to peak, and T subscript B is called the time base of the hydrograph. Okay. There is one more thing which we have not defined here, is called the time lag. Let me write it first. It's called the time lag or basin lag. Okay. This time lag is nothing but the time between the centroid of the effective rainfall hydrograph and the point of inflection on the hydrograph. So, if I take the, and D is, let us say, the point of inflection of the hydrograph, this time is called basin lag. All right. This is the time delay of the basin. It responds after that much time. So, it is synonymous or equivalent to time of concentration in most of the cases. Okay. So, these are the basic elements of a storm hydrograph. All right. And what we will do next is we will look into some of these components, for example, the rising limb and so on. So, if we look at the rising limb, of a storm hydrograph, it is also known as the concentration curve. Okay. What is the concentration curve or the rising limb? Basically, we see that there is a initially there is a small rise in the runoff volume in the catchment, all right, or in a river, and then it becomes very steep. All right. So, what is happening when the rain is falling is that different components or storage components are getting satisfied, or they are getting filled up. All right. As a result of that, the catchment is releasing some water from its storages, mainly the surface storages. All right. So, what you see as the rising limb is basically the release of water due to gradual increase in the storage of the catchment. Okay. So, the rain is falling continuously. All right. There is an intense storm. Catchment is holding some water. All right, but it is not able to do it because the capacities are getting satisfied. So, it slowly starts to release some water. All right. So, as the rain is increasing, we are seeing some water at the outlet of the catchment, and that rate of that water will keep on increasing slowly with time. Another important point to note for the rising limb is that initially it rises slowly. There is a slow rise. Okay. Why is there is a slow rise in the beginning of the rising limb? Because we have higher infiltration. Very good. All right. Due to high infiltration. At the beginning of a storm, there will be certain initial conditions. The catchment may be either dry or it may be 10, 20, 30% saturated. All right. So, there will be more infiltration in the beginning, and you see, if I go back, that you see that this portion, this is rising very slowly. All right. Then later, very steep rise due to low infiltration in the catchment. Okay. So, you have rising limb rising very steeply towards the later portions because of the little or no infiltration and catchment getting saturated in most of the components. As we can see that the rising limb is a function, or its size and shape and steepness will depend upon both the catchment characteristics and storm characteristics. Okay. What do we mean by that? The length, the steepness, the size and shape and everything related to the rising limb will depend upon the, let us say, size of the catchment. If the catchment is, if you compare two different catchments, one is of small area, other is of large area. The small area, same rainfall if you apply, it will start to rise very quickly. So, it will be steeper as compared to a larger one. All right. Similarly, it will also depend upon the storm characteristics. What do we mean by that? If we apply a higher intensity of rainfall, then obviously you will have a steeper rising limb, right. So, it depends both on the catchment characteristics and on the storm characteristics. Then the next is the crest segment. As you can understand, we are close to the peak of the hydrograph. At that point of time, all the catchment area is contributing runoff at the outlet. All right. So, most of the area is contributing. So, you say various portions of catchment contribute runoff at the outlet. The peak will occur after the storm. Okay. All right. Note that the peak will not occur before the rainfall has stopped. All right. Peak will occur only after rainfall has stopped. Okay. We may also have situations of what is called multiple peaked crest segments. Okay. When can we have the multiple peaks? Let us say you have a rainfall event, it stopped for some time, and then there is another rainfall event. Okay. So, you have the rising limb rising, then it started to go down, but then it will go back up again. All right. So, you have multiple peaks in the catchment. Okay. Then the third important component of a storm hydrograph is called the falling limb. Where is the water coming from when we are on the falling limb? It is mainly different storage components. Okay. It may be surface, it may be subsurface, it may be deep groundwater. So, basically you have depletion of different okay, which is contributing water on the falling limb of a storm hydrograph. Will it be a function of storm or the rainfall characteristics, that is intensity of rainfall and duration of rainfall, etc.? No. Okay. The falling limb will be a function of the catchment characteristics only. Okay. So, it will depend upon the holding capacity and how it is releasing the water out of these different types of storages. Then this falling limb or the recession. Okay. So, the next portion is as we were looking at is the falling limb of a storm hydrograph, and there is a mathematical equation that was proposed by Horton in 1933, and that is what we will look at next, which is called the recession curve. This recession curve is actually also known as In different books you will find different terminology used for the falling limb. It's called normal depletion curve, or master base flow recession curve. So there are different use for this recession curve, and the equation is same, and this is how we model the flow at any time t on the falling limb as q0 times e to the power minus t minus t0 divided by k. Okay. In this equation, your qt is flow at any time t on the falling limb. Q0 is the initial flow, okay, at the beginning of the falling limb. T is of course time, any time after T0, and T0 is the time for Q0, or when the flow Q0 starts, or when your time begins on the falling limb. And K is called an exponential constant. Okay. And we'll name this equation as 5.2.1 as per the convention we have been following from the book, Venti Chow's book. Okay. This equation has been based on the assumption of catchment behaving as a linear reservoir. That is, the storage in the catchment at any time t is some constant times the outflow at that time. Okay. What is a linear reservoir? We have seen earlier, when the storage and the outflow from the catchment are linearly related with each other. Okay. Next, we move to base flow separation techniques. Methods. Okay. I'm sure you may have looked at the base flow separation methods in your undergraduate hydrology also, but we will revisit some of these methods. Okay. Basically, there are three methods we are going to look at, okay, which differ in certain assumptions, and depending upon those assumptions, when they are valid, they will be used in different types of situations in the field. Okay. First one is called the straight line method. What we do in the straight line method is we find the beginning of the storm hydrograph. All right, let's say that point is A, and we estimate the end of the runoff. Let's call that B. All right, end of the runoff, and after that base flow will be occurring in the river. And then we simply join these 2 points by a straight line, and this method is called the straight line method. So A is the start of your direct runoff hydrograph, DRH is your direct runoff, B is the end of DRH, and this type of method is applicable to ephemeral streams. Okay. When we have hardly any contribution from the base flow. All right. So you have very little contribution, and then You can join the beginning and end point by simple straight line. Second method is called the fixed base method. The problem with the first method, that is the straight line method, is that we don't know when the DRH will end. All right, this is just based on some experience or judgment. All right, we will try to locate the point B on your hydrograph. All right, and depending upon the person, there is some subjectivity involved. All right, some people will take B here, some people may take it slightly around in a different position. So what the fixed base method does is it gives you an equation to locate that endpoint B. Okay. So beginning there is no point. All right, start of the hydrograph is A. Okay, then we draw a line at the peak. All right, and then we define N. Let's say this is B, which is located N days after the peak has occurred. All right, so what is N? N is the number of days after the peak. All right, so we know when the peak has occurred, and the equation for N is given like this. It's 0.83 A to the power 0.2, where A is the area of the catchment in square kilometer. All right, so what we do is we have located the points A and B. All right, now what we do is we take the previous hydrograph, all right, and then we just extrapolate it. All right, and find the point of intersection of this extrapolated hydrograph with the line drawn from the vertical, and then we join this point with the end point B. Okay, so what we are doing is we extrapolate the previous hydrograph and join intersection of extrapolation or extrapolated line and vertical from peak discharge. All right, with point B or the end of the hydrograph. All right, so what we are doing is we are trying to find the point of intersection of the vertical drawn from the peak and the extrapolated hydrograph from the previous hydrograph, and then we join with point B. This type of method is applicable for bigger catchments. And also flatter catchments. Okay. Why do we say that? If I applied the first method, let's say, on this, all right, and we compare the straight line method and the fixed base method, the straight line method is giving me higher base flow, all right, as compared to the fixed base method. All right, so this is your, let's say, method 1, and this is your second method, and the second method is giving you less amount of base flow. All right, that can occur from bigger and flatter catchments. Okay, so that's why it is applicable to the bigger and flatter catchments. The third method is called the variable slope method. Okay. In this, what we do is we extrapolate the previous hydrograph, get the point of intersection like we did earlier, and then we also extrapolate the next hydrograph. Get another point of intersection drawn from the point of inflection. Okay. So, A and B are your start and end of the direct run of hydrograph, P is your peak and D is your point of inflection. So, you draw the vertical from peak and from point of inflection, you extrapolate the previous hydrograph to some point and then get that intersection and join these two intersections which we have got. Okay. So, basically what we do is we forward phase flow is extrapolated back. Okay. Means from B going back and finding the intersection with the vertical from D, and the backward or the previous base flow is extrapolated in front. Okay. Points of intersection are found with verticals from P and D as shown in the figure as we have discussed, and then both of these intersection points are joined by the simple straight line. Okay. There is another variation in this method in which the point A is joined by the vertical drawn from D by a smooth curve like this. Okay. So, there are two different variations. In the first one we just join the two points of intersections, and other one we just simply join point A with vertical from the D. As you can see that in this method what we are doing is we are giving more importance to the base flow that is occurring just after the peak. Okay. You may have a situation in certain catchments in which you may have base flow contribution during the storm just after the peak or around the peak. All right. The earlier two methods are not allowing us to do that. Okay. So, this method is applicable to moderately sized catchments in which there is quicker base flow appearing during the storm. Okay. So, as we see, there are three different methods and all three will be applicable in different types of situations. Now, we move forward and we will define the concept of what is ERH, and I think we all understand this is effective rainfall heatograph. Right, and this gets converted into what is called a DRH, which is direct run of hydrograph. Okay. How do we find the direct run of hydrograph given an ERH? All right, there are various methods. All right, we will get started with a very simple concept. All right, which you have probably seen in your undergraduate classes again, and this is called the phi index. Okay, what is phi index? It is nothing but a very simple concept in which we have the rainfall heatograph and we draw a horizontal line on it such that everything above that line is direct runoff and everything below is abstraction or the losses. Right. So, if you want to look at it graphically, all right, if this is your rainfall heatograph, you just draw a line like this and let us say we call it phi index. Okay. Anything above is this is your DRH, and anything below that is your losses. Okay. So, how we define this phi index is, it is a constant rate of infiltration, and its units obviously would be L by T. That would yield an ERH, or effective rainfall heatograph, with a total depth of your ERH that is equal to the depth of your direct runoff. And which we define as RD. Okay. So, the total depth of direct runoff is RD. Okay. And this is how we define this relationship. Your RD, or the depth of direct runoff, would be equal to summation small m varying from 1 to capital M of Rm minus phi delta T. Okay. And this is your equation 5.3.1 as per the convention we have been following. Okay. In this equation, it is important to understand some of these variables. Rm is the observed rainfall. Time interval m, or the mth time interval, that is. Okay. And units again are in centimeters or inches or whatever. RD is the depth of direct runoff. Okay, same units. Phi is your phi index, of course, and capital M, which is, I would like to emphasize, it's very important, is the total number of intervals that actually contribute runoff. Okay. This is very important to understand what is capital M. All right. In the next class, we will take up an example on how to calculate phi index and what is capital M. All right. This will not be equal to the total number of rainfall intervals. Right. It may be less than that. Right. So it is important to understand that.